An AI inference cluster is a coordinated set of compute resources that serves requests to already trained models. Those resources may be several computers, several GPU servers, or a mix of GPU and CPU nodes behind a shared interface. The cluster accepts prompts or other inputs, selects an appropriate model and worker, performs inference, and returns results while managing competing demand. Its purpose is operational capacity, supporting more models, users, or simultaneous jobs than one serving process can handle reliably. It helps to distinguish three scales. A single workstation has one operating system instance and is the simplest system to secure and maintain. A multi-GPU server scales up inside one machine, sharing memory pathways, storage, and management while gaining additional accelerator capacity. A distributed cluster scales out across networked nodes. Scaling out can increase aggregate throughput, isolate model roles, and add resilience, but it introduces routing, queuing, network dependencies, configuration drift, and failure modes that do not exist on one host. Use cases range from a local lab that shares a few models across a team, to a small business hosting private assistants, to an enterprise platform serving many applications. Hybrid designs can keep sensitive inference on premises while bursting approved workloads to cloud capacity. The design should follow data sensitivity, latency, cost, and availability requirements rather than a desire to imitate the largest deployment. A cluster does not combine unrelated GPUs into one unlimited pool automatically, and it does not guarantee faster individual responses. It adds capacity only when software can place work effectively and the network, storage, and operations models support that placement. Treat the cluster as a distributed service, not a pile of accelerators. Its value comes from coordinated behavior that remains measurable, secure, and supportable. Define the service before designing the cluster. Identify who will use it, which applications will call it, and when demand occurs. 10 analysts using interactive chat create a different load from an overnight document processing pipeline. Inventory model types, quantizations, context lengths, embedding workloads, and any vision or multimodal processing. Each combination has distinct RAM, system memory, storage, and acceleration requirements. Separate latency from throughput. Latency is the time a user waits for useful output, including queuing, prompt processing, and generation. Throughput is the amount of work completed over time. Batching may improve total throughput while increasing the wait for an individual request. Define targets such as acceptable time to first token, requests per minute, concurrent sessions, and maximum queue depth. Use representative prompts because short synthetic tests can hide the cost of long contexts. Document privacy, uptime, and recovery expectations. Determine where prompts, retrieved documents, model outputs, and logs may be stored or transmitted. Decide whether planned maintenance is acceptable, whether a failed node must be bypassed automatically, and how long service restoration may take. Convert budget into more than purchase price. Include network equipment, storage, support time, software, power, cooling, rack space, and expected utilization. Finally, challenge the cluster assumption. A larger single server, scheduled access to one workstation, or a managed service may satisfy the requirement with less operational burden. Build a cluster when measurements show a need for independent model roles, aggregate concurrency, fault isolation, or horizontal growth. Requirements protect the project from solving an imagined scale problem while overlooking the cost of operating a real distributed system. A practical starting pattern is one front end with multiple inference nodes. The front end provides a stable user or application interface, while each worker hosts a model server. A router or load balancer sends requests only to workers capable of serving the requested model. Replicating the same model across several nodes increases concurrent capacity and creates options for maintenance or failure, provided the routing layer removes unhealthy instances promptly. Another pattern assigns separate model roles. One node may serve a general language model, another a coding model, and a smaller CPU or GPU service may generate embeddings or re-rank search results. Role separation makes resource use predictable and prevents a large model from evicting smaller services. CPU support nodes can host APIs, queues, databases, observability, and retrieval components, preserving expensive GPU capacity for inference. Storage and management may also be separated. A storage node can hold controlled model versions and distribute them to local worker caches. A management node can provide configuration, monitoring, secrets, and deployment coordination. Avoid making either service an undocumented single point of failure. Define what happens when shared storage, the router, name resolution, or the management plane is unavailable. Local clusters favor privacy and predictable ownership. Cloud clusters favor rapid provisioning and elastic capacity. Hybrid designs can combine them, but data classification and routing policy must make the boundary explicit. Start with the fewest roles that meet the requirement. Add replication, queues, and management services in response to observed failure or capacity needs, because every architectural box becomes software that must be secured, monitored, upgraded, and recovered. Size each worker for the models it will serve. GPU architecture determines supported acceleration features, while VRAM determines whether model weights, context cache, and runtime overhead fit. More GPUs do not create shared memory automatically. A runtime must support tensor or pipeline parallelism to divide one model across devices, and cross-device communication may become the bottleneck. Replicating a model on separate GPUs is often simpler when the goal is concurrent capacity. CPUs handle tokenization, request processing, data movement, and services that surround inference. System IRAM must accommodate model loading, caches, and non-GPU components without swapping. Use fast local SSD storage for active model copies when possible. Repeatedly loading large models over a shared network can delay startup and turn storage into a cluster-wide dependency. Network design follows traffic patterns. Small text prompts may use little bandwidth, but model distribution, multimodal inputs, logging, backups, and distributed inference can move substantial data. Measure both bandwidth and latency. Choose switches with enough non-blocking capacity, appropriate port speeds, and management features for segmentation and monitoring. A fast link cannot compensate for an oversubscribed switch, poor cabling, or a design that transfers model state unnecessarily between nodes. Account for physical infrastructure. Confirm power circuits, outlet distribution, power supply headroom, heat removal, airflow, and noise before installing dense compute. Rack systems improve serviceability and cable management, while desktop systems can be economical for a small lab. Consumer hardware may offer strong performance per dollar, but usually has fewer remote management, redundancy, validation, and support features. Document those trade-offs rather than assuming low purchase cost means low operational cost. The serving runtime turns model files and accelerator resources into a network service. Llama.cpp server is portable and effective for quantized models across CPU and several GPU backends. A Llama packages model management behind a straightforward local service. These tools are useful for labs and modest deployments where operational simplicity matters more than maximizing concurrent throughput. VLLM is designed for high-throughput language model serving and includes memory management and batching techniques suited to concurrent requests on supported hardware. Text Generation Inference, often called TGI, is another production-oriented server with model serving and observability features. Their advantages appear only when models, accelerators, and traffic patterns are compatible. Benchmark the actual model and prompt distribution. Do not select a runtime solely from an impressive result produced on different hardware. An OpenAI-compatible API can decouple clients from the underlying server. Applications use a familiar request format while a gateway or router directs traffic to llama.cpp, a Llama, VLLM, or another backend. Compatibility is not always identical across parameters, streaming, tool calls, embeddings, and error behavior, so test the features your clients depend on. Open Web UI can provide a shared browser front end, but it should use the same authentication and routing controls as other clients. Introduce model routing only after one server is reliable. Start a known model, confirm acceleration, measure latency and throughput, exercise health checks, and document startup and shutdown. Then replicate the service or add another model role. Complex orchestration cannot repair an unstable serving process. It only distributes the instability. A simple, observable serving layer is the foundation for safe scheduling and scale. Routing begins with capability. A request should reach a node that has the requested model loaded, supports the required context and features, and has enough available memory. Within that eligible group, the router may choose the least loaded instance, follow a weighted policy, or preserve session affinity when a workflow depends on local state. Health checks must remove failed or degraded nodes quickly without sending traffic into a restart loop. Concurrency describes simultaneous work. Each active sequence consumes cache and compute, so accepting more requests can reduce per-user speed or exhaust memory. Queuing protects the server by holding work until capacity is available, but queue delay contributes directly to latency. Establish maximum queue depth, request timeouts, and admission controls. When the service is saturated, a clear busy response is safer than allowing every node to become unresponsive. Batching groups compatible work to improve accelerator utilization and total throughput. The trade-off is that a request may wait for a batch and share compute with others. Interactive chat usually prioritizes low time to first token, while offline processing may accept delay in exchange for higher throughput. Separate service classes or queues when one policy cannot serve both workloads fairly. Failover is more than pointing at another IP address. The alternate node must have the correct model version, configuration, capacity, and dependencies. Test what happens to in-flight requests and whether clients retry safely. Track arrival rate, service time, queue time, rejection rate, and resource saturation. Scale only after identifying the constrained stage. Adding a GPU worker will not fix a slow shared storage service, an overloaded router, or a network path that cannot carry the traffic. Model storage should balance control with startup performance. A managed repository can hold approved model versions, checksums, licenses, and configuration metadata. Workers can copy approved artifacts into local SSD caches, so inference does not depend on sustained access to shared storage. Define cache size, eviction policy, and how a worker verifies that its local copy matches the version advertised to the router. Use explicit version identifiers rather than immutable labels such as latest. Model weights, quantization, tokenizer, prompt template, runtime, and serving parameters together influence behavior. Record that combination, so results can be reproduced and a problematic release can be rolled back. Stage model changes on limited capacity, run representative evaluations, and promote only after functional and performance checks pass. Separate model artifacts from private operational data. Prompts, outputs, uploaded files, embeddings, vector indexes, and logs can contain sensitive information even when the model weights are public. Apply access controls, retention schedules, encryption, and backup policies according to data classification. Avoid placing private data in a broadly readable model share simply because every worker can access it. Back up what cannot be recreated. Configuration, routing policy, secrets references, evaluation results, metadata, and authorized private datasets. Large public model files may be restored from trusted sources if their exact versions and hashes are recorded. Test restoration rather than equating a completed backup job with recoverability. Storage design succeeds when a new or recovered node can obtain the right model safely, start predictably, and avoid exposing unrelated data. Require authenticated access at the cluster boundary and authorize clients for specific models or service classes. Protect APIs with encryption in transit, rate limits, and network controls. Segment user-facing gateways, management interfaces, storage, and worker traffic. so compromise of one component does not expose the entire control plane. Store service credentials in a managed secret system, rotate them, and avoid embedding them in images or scripts. Patch operating systems, GPU drivers, runtimes, front ends, and orchestration components through a controlled process. Remove one node from service, apply the change, test health, and representative requests, and expand the rollout only when results are acceptable. Maintain rollback packages and configuration snapshots because a syntactically successful update can still change model behavior, memory use, or throughput. Monitor from the request down to the hardware. Track availability, error rates, queue time, time to first token, generation rate, and end-to-end latency. Correlate those signals with GPU utilization, RAM, CPU, RAM, disk, network, power, temperature, and throttling. Health checks should detect whether a process is merely running and whether it can actually answer a model request. Alert on user impact and sustained resource conditions rather than every brief fluctuation. Prepare for incidents. Preserve useful logs without retaining sensitive prompts longer than policy allows. Define how to isolate a node, revoke credentials, stop abusive traffic, restore a model version, and communicate service degradation. Review cost and energy consumption alongside performance. Idle accelerators and overloaded cooling are operational signals. A secure cluster is one whose normal state is visible, whose changes are controlled, and whose operators can recover from failure without improvising access or data handling. An AI inference cluster is an operational system, not simply a collection of GPUs. Its design begins with users, models, data sensitivity, latency, throughput, concurrency, uptime, and budget. Those requirements determine whether a cluster is justified at all. A single server remains the better answer when it can meet demand with acceptable recovery and less management overhead. When scale-out is justified, choose the simplest architecture that satisfies it. Use stable model servers behind a controlled interface, route requests only to compatible healthy nodes, and make queuing and overload behavior explicit. Match GPUs and RAM to model roles, support them with sufficient CPU, RAM, storage, network capacity, power, and cooling, and understand where consumer components trade lower cost for fewer operational features. Manage model weights, tokenizers, templates, runtimes, and configuration as version releases. Keep active models in local worker caches when that improves startup and resilience while maintaining an approved source of truth. Separate those artifacts from prompts, embeddings, logs, and private datasets. Back up your placeable configuration and data and test recovery. Finally, secure and observe the whole service. Authenticate clients, segment management paths, protect secrets, control patches, and monitor both user experience and hardware health. Build rollback and incident response into routine operations. Start with measured demand, establish a repeatable baseline, and scale the component that evidence identifies as the bottleneck. That discipline produces a cluster that delivers dependable capacity instead of multiplying cost and failure modes.